SPH4U, energy and momentum, 3.8 different forms of energy. So thermal energy is created by the force of friction and is given by this equation, ETH. So thermal energy is equal to Fk times delta D. Fk, that is mu times Fn. Mu is the coefficient of friction and Fn is the normal force. So a 19.9 kilogram box slides to stop after 28.8 meters. The coefficient of friction is 0.105. So how much thermal energy is produced? So let's draw a free body diagram. So you have the force normal going upwards from the box, force gravity going downwards, and you have force friction here. So ETH, so we know this is equal to Fk times D. So we know that's actually equal to mu times mg. Mg is the force of gravity and it has the same magnitude as a normal force. So that's times d. So the distance, so that comes out to be 0.105 times 19.9 times 9.8 times 28.8. So that means that ETH, the thermal energy produced, is equal to 589.74 joules. So now we have to determine the initial speed of the lock. So we can use this, find this using the conservation of energy. So EK1 plus ETH1 is equal to EK2 plus ETH2. So we know that the first thermal energy is equal to 0, and that's because it's not moving yet, so there is no friction. And yeah, so, and we know that the final kinetic energy is also equal to 0 because it's no longer moving at the end. So EK1 is equal to ETH2. So 1/2 mv squared is equal to 589.74. So if we use some algebra to rearrange this, the square root of 2 times 589.74 over the mass, which is 19.9, is equal to the velocity. So that means the velocity is equal to 7.7 meters per second. So the initial speed of the box is 7.7 meters per second. So now we'll be moving on to elastic potential energy. So this has to deal with springs. So there's something called Hooke's law, which states that the magnitude of the force exerted by a spring is directly proportional to the distance the spring has moved from equilibrium. So that's given by this equation. F of x is equal to negative k times x. So this is the force exerted by the spring. And this k is the spring constant. It will be given in newtons over meters. And this is x, the distance from equilibrium. So equilibrium is the resting position of the spring, and you can pull it out or compress it, and the distance away from equilibrium, that will be the x. So this is the spring in equilibrium, and now we are compressing it. Now we're pulling it, so that gives this distance x. If we compressed it to like this, then there would be this distance x. Just, it will depend on the reference frame that you're using as to whether that will be positive or negative. So yeah, this is the force exerted by a spring, and in order to find the elastic potential energy, it's given by this equation. E is equal to 1/2 k times x squared. So k is still a spring constant, and x is the distance from equilibrium squared, and yeah. And that is measured in joules like any other form of energy. So elastic potential energy is the energy stored in an object that is compressed or stretched or bent or somehow misshapen. So this is quite an interesting example of a question that deals with elastic potential energy. So an apple of mass 100 grams is attached vertically to a spring with a spring constant of 9.6 newtons over meters. So how much elastic potential energy is stored in the spring when the apple has fallen 11 centimeters? So first let's draw this. So we have spring, have the apple here. So this is equilibrium, x is equal to 0. So now it has gone down 11 centimeters. So that's 0.11 meters. So it's gone this far. So use equation E is equal to 1/2 kx squared. So that's equal to 1/2 times 9.6 times 0.11 squared. That comes out to be 0.058 joules. So now we need to find what is the speed of the apple once it has fallen those 11 centimeters. So in order to do this, we will need to use the conservation of energy equation. So since this is vertical, we had to use gravitational potential energy as well, which is very interesting. So we have Eg1 plus Ek1 plus E1 is equal to Eg2 plus Ek2 plus Ee2. So Ek1 gets crossed out because V1 is equal to 0. Ee1 gets crossed out because x is equal to 0 at this point. And Eg2 is equal to 0 because h is equal to 0. So all we're left is Eg1 is equal to Ek2 plus Ee2. So this makes this quite a bit more simple. So mgh is equal to 1/2 mv2 squared plus 1/2 kx squared. So it's this v that we're looking for, this v2. So if we do some algebra, we can get this expression 2 times mgh minus 1/2 kx squared all over m, and all square rooted, is equal to v2. So let's just move up here so it has some more space. So we have 2 times 0.1 times 9.8 times 0.11, and all this minus 0.058 divided by 0.1. That is all equal to V2. So 0.99 meters per second is equal to V2. So yeah, that is the speed of the apple once it has fallen those 11 centimeters. So simple harmonic motion is when a mass is moved back and forth through an equilibrium on a spring. So when the elastic potential energy is max, the kinetic energy is 0. And when the elastic potential energy is 0, the kinetic energy is max. And there's also, you can also find the period of this motion, and that is t is equal to 2 pi times the square root of m over k. M is the mass in kilograms, k, that would be the force constant, and 2 pi, that is 2 times 3.14, so 6.28. So yeah, and t is the period in seconds, and frequency is always equal to 1 over t. So here's an example of simple harmonic motion question. So a ball of mass 0.55 kilograms undergoes simple harmonic motion with a force constant of 120 newtons over meters, and the total mechanical energy in the system is 7 joules. So what is the distance from the equilibrium? So in order to find x, we need to look at it when EE is max. So we know that the total mechanical energy is 7 joules. So that means that 7 joules is equal to the kinetic energy plus the elastic energy. So EE plus EK is equal to 7. So EK, we can cross that out because when EE is max, EK is equal to 0. So 7 is equal to 1/2 kx squared. So that means that 2 times 7 over 120 whole square rooted is equal to x. So that turns out to be 0.34 meters is equal to x. So what is the max speed of the box? So in order to find the max speed, we'll look at it when EK is max. So we would do 7 is equal to EE plus EK. This time we would cross out the EE because when EK is max, EE is equal to 0. So 7 is equal to 1/2 mv squared. So that comes out to be the square root of 2 times 7 over 0.55 is equal to v. So 5 meters per second is equal to v. So what's the speed of the ball 10 centimeters away from equilibrium? So we would use the same base equation. 7 is equal to 1/2 kx squared plus 1/2 mv squared. So 10 centimeters is not the farthest away from equilibrium it could be, and thus we do not cross either of them out. So we just do some algebra to solve for v. So v is equal to the square root of 2 times 7 minus 1/2 kx squared over m. So v is equal to 2 times 7 minus 1/2 times 120 times 0.1 squared over 0.55. So velocity comes out to be 4.7 meters per second. And now what about the period? So t is equal to 2 pi times m over k. So t is equal to 2 pi times the mass, which is 0.55 over k, 120. So t is equal to 0.43 seconds. So that is how you would approach a simple harmonic motion questions, and that was the end of SPH4U Unit 3. Thank you.